So, calculus of polar equations. I want to start by looking at how to find the area bound by a polar curve. Area bound by a polar curve. So let's start with one. So here's our polar axis. Here's our origin. And here's the deal. We know that our polar curves are given by an angle, and that angle dictates what the r is. So basically, a polar curve can be defined arbitrarily by saying, we're going to start at some angle, let's call it alpha. We're going to end at some angle, call it beta. And we have some curve. R is a function of theta. What we're going to try to find here is we're going to try to find the area that's bound by this polar curve. The area would be, do you see where the area is going to be? Mm-hmm. It's not going to be this area from the polar axis to here. What the area we're looking at is, it says, well, we're starting here, aren't we? We're going to here. The curve is here. It's this. That's the area that we're looking at. That's the area bound by a polar curve. Show of hands if you understand the idea of it. Do these symbols make sense to you? It says that we're going to start at a certain angle, alpha. We're going to end like 8, except it's not linear, so we're going to say that this is alpha, it's an angle. We're going to end at another alpha, beta, no problem. We're going to go along this curve, r. R is a function of theta, and the area that's bound by that, it's kind of like a cone, but it depends on this curve. You see the cone I'm talking about? Actually, it's more like a sector. We're going to talk about that in a second. So here it is. How we find the area. I'm just going to give it to you. And you're going to see why it's going to be very straightforward right now. Here it is. Now, these functions, are they based on x? No. Are they based on y? No. They're based on... So when we integrate, remember the area is always an integral type of idea. So we're going to, integral says we're adding up a whole bunch of slices of stuff. We're going to talk about what slices we're adding up in just a second. I'm not going to prove it for you because I think I can just explain it well enough. If you remember anything about Calculus 1, when you do integrals, the Riemann sums that you added up, they were little slices, little rectangles. Remember that? You add up an infinite number of them. We're going to do the same idea. That's what integral does. It adds stuff up. So here's what we're going to add. We're going to say, well, where do we want to start? If it's not x and y, we got to start at some alpha. So we're going to start here. We're going to end at
beta.
And we're going to have, here's what we're going to have. If you think about this, what we're really doing is we're finding the area of a little teeny sector. The area of a sector is given by this. If you've seen that before, that's the area of a sector. It's 1/2 r squared theta. You can look it up. It's a formula. I'm not going to go through the proof of that formula, all right? That's the area of a sector. It says take half the radius squared and then multiply by whatever angle you have. Well, here's what we're going to do, okay? Are you listening? Now, r is a function of theta, isn't it? So for us, it says what we're going to do is we're going to take a real teeny little sector of this thing, a teeny little one. And then we're going to find the next one, and the next one, and the next one, and the next one. We're going to allow that distance, that angle, the distance of the angle between them to go to 0. And if that's the case, we're going to have an infinite number of teeny little sectors that we're going to add up. So when we're saying we're starting at alpha, you're going to have all these sectors starting at alpha, adding up to beta. And we're going to say, all right, cool. Well, we're going to have the 1/2. We're going to have a function. We're going to let r change based on theta. R is a function of theta. But then we're going to integrate with respect to theta. And the reason why we integrate with respect to that variable is because when you integrate that, like a dx, that's saying that dx, the distance between the x values are like infinitesimally small, giving you an infinite number of rectangles when you do a basic area. For us, it says we're going to do d theta, saying that our angle is infinitesimally small. We're adding up an infinite number of little sectors. We're letting the angle change little by little by little by little by little. So if you understand the idea there. So where's this coming from? chirp, chirp, little crickets. Where's that coming from? Area of a sector. Do you guys see the area of a sector I'm trying to show you here? This is the area of a sector. You're just allowing the angle to change. That's all you're doing here. Make sense? It's cutting this into really little teeny sectors, adding up the sectors from alpha to beta. So this is adding up. Remember, the integral is like an S. It comes from a summation notation. So the integral is, we're adding up all the teeny sectors here. See it?
Yes.
Teeny sectors adding from alpha to beta. That's what it means. So let's do an example real quick to illustrate this. It's better to know where the formulas came from than to not know. So I want to find the area bound by r squared equals 4 cosine 2 theta. Before you say, what in the heck is that? I don't even know where to go. We've seen this before. In fact, in the last section, we graphed that. It didn't look exactly like this. It looked like this. It looked like r equals the square root. I messed up already. It looked like this. R equals 2 square root cosine 2 theta. Is that ringing a bell at all?
Yeah.
That was the last example that we graphed. All right. So what this graph looks like, and you could probably just see it if you thought about here. If I plug in 0, look at this. If I plug in 0, it's 2 times 0. I'll take it, and then cosine 0, and then 1 times 4.
4.
And I take square root of it.
2.
Is r squared. Yeah. So if I do angle of 0, I got 2. Remember that at all?
Yes.
And I plugged in pi over 2 pi over 4. 2 times pi over 4. Say it again. Yeah, you're right. Pi over 2. Cosine pi over 2. 0 times 4. R squared. R equals 0. So we got to here. And we learned about the symmetry. We learned that anything past pi over 4 was undefined. Do you remember that? So we said, okay, well, that can happen. So what we got really was this shape that did this. Well, that's pretty good for me. Just make the points bigger.
Applause.
I know, right? That's pretty good. Just don't look at that one. Well, here's the deal. If we know that's what that looks like, and we know about the symmetry, I'm not going to reinvent the wheel, okay? If you want to figure out how to actually graph that thing well, you'd watch the last section, okay? Because we've already done this. We know it's symmetric about the polar axis. We know it's symmetric about the theta equals pi over 2 axis. You with me? So let's think about this. When we plugged in theta equals 0, it gave us 2. When we plugged in theta equals pi over 4, it gave us 0. Does that make sense? So our angles go from 0 to pi over 4, and it gives us this little lobe right here. Gives us that lobe. Now let's use that to our advantage. If we use it to our advantage, well, let's set this thing up. I want to find the area bound by this curve. What that means is all of this stuff. Do you understand? It does not look like it from my picture, but you get that this and this and this and this are all the same area.
Yes.
How many pieces are there?
4.
So if we integrate from 0, where do I want to go? 0 to where? Pi over 4. Pi over 4 moves me from here to here. That's where I want to go. So if I did 0 to pi over 4, how many pieces is this going to give me from 0 to pi over 4?
4.
No, from 0 to pi over 4, it's giving me
1.
just this piece. What do I have to do to make all of it?
4.
Multiply it by 4. Show of hands if you understand that concept. Are you sure? Yes, no? Yes? Okay, so we said I know from probably the previous sections how you'd graph this. You know, you go back there, you figure out how to graph it. I did it very fast here because for the sake of time. We know that at theta equals 0, I get 2, so I'm starting here. At theta equals pi over 4, I was at 0. So from 0 to pi over 4, I get this little lobe. If I multiply 1, 2, 3, 4, and just go from 0 to pi over 4, I'm going to have the whole entire area of that shape. You get me? Now, use the formula. What's our formula to start? 1/2, very good. And then? Now, be smart about this. Look at, we already have r squared. So if this is r squared, I'm just going to have 4 cosine 2 theta. See if you're really just paying attention. Should I square that, yes or no?
No.
Because this is r squared. And then d theta. Wrap that thing up with a d theta. Show of hands feel okay with that one. Okay, let's make this thing nicer. What are we going to do? Probably take the 1/2 out. Also going to take the 4 times 1/2 times 4 is? We're going to get 8. 8 integral 0 to pi over 4 cosine 2 theta. Oh my gosh. Have you done stuff like this in this class?
Yeah.
We covered chapter 7. Yay! You know how to do integrals of trigonometric functions. Do it. What would you use for that? Is it a hard one? No, it's an easy one. What would you use? What would you use?
Substitution.
Ah, good, yeah. A U substitution is what you would use. Yeah, you do it. In fact, I'd probably do it in my head, because at this point you probably can do that. So when I would do this one, I'd say, okay, here's my 8. The integral of cosine is sine, not negative sine. Verify that? Sine of whatever's under my hand divided by the derivative of whatever's under my hand, which is just 2. The 2 goes on the denominator. Do you understand that? A U sub says, hey, take the derivative of that and divide by it. That's basically what we're doing here. What now?
8 simplifies with the 2.
Yeah, let's simplify. Okay, so we're going to have 4 sine 2 theta, and now what? Yeah, let's go for our actual evaluation. 0 to pi over 4. Can you plug that in? Hello, yes, no? That should be pretty easy. So we're going to have 4 times sine of 2 times pi over 4 minus 4 times sine of 2 times 0. Well, that should be pretty straightforward. What's 2 times pi over 4? Good. What's sine of pi over 2? And 1 times 4 is?
4.
What's sine of 0? So this whole thing goes to 0. This thing goes to 1. We get 4 times 1. What's really, really interesting, the area that's bound by this polar equation, this polar curve, is equal to... Does that blow your mind? That it's not some random weird decimal that doesn't end? The area is 4. That's crazy. What's the area of one of these things? 1. 1, yeah. 1, 2, 3, 4. That's neat. Show of hands if you understand that one. Okay. Tell you what, let's do one more. We can just do as many as we can. So area by r equals 1 plus cosine theta. We've seen that several times now. What is that?
The butt.
Come on, I should have said that to you. What is that? It's cardioid, that's right.
So you said it was facing up because it's pluses.
At first I said a heart, you said a butt.
It's like the butt's up on the top or on the bottom.
This is sideways.
This is the laying down.
This one is
It was this one.
the spooning one, whatever.
It was this one. Mine looks retarded, but it's okay.
That one.
Oh, okay.
That's that one. I think I drew it backwards a little while ago. Didn't I?
Yeah.
I did draw it backwards. Oh, shame on me. Darn it. Oh well. Doesn't really matter. That was your name. So, that's a cardio. Then that makes a lot more sense for our slope anyway. Whatever. So, let's find the area bound by this cardioid. Now, there's two ways that you can do this. Firstly, do you understand the cardioid is symmetrical? So if I, make sure I get it right, my dyslexia is kicking in. If I have that, if I have that point is at theta equals 0, and this point is at theta equals pi. That's right. So I can do this one of two ways. The first way I could set this up, we could set up the integral from, we could do it from 0 to 2 pi. That would actually work. So if you want to go from 0 to 2 pi, that's fine. Let's set up that way first. So if I went from 0 to 2 pi, that would be the entire region, all at once. Are you listening?
Mm-hmm.
All at once. Let's do the formula. What would be inside of there?
1/2.
Okay, the 1/2 is there. Very good. And then what?
1 plus cosine quantity squared.
Where are we getting the 1 plus cosine theta from?
R
Uh-huh.
squared.
Oh, why do we have to square it?
Because R is not squared.
Okay, very good. So this is 1/2 r squared d theta. Show of hands if you feel okay with that one. Now, if you work this out, you're going to get exactly the same answer as if you were to do this one. So let's change our thought process a little bit. Let's say that I don't want to figure out the whole thing at once. I just want to figure out this one. Do I still go from 0 to 2 pi? Where do I go from?
0 pi.
And then what do I do?
Multiply by 2.
So that is another option that you could do. There's a couple ways to do this because there's a lot of symmetry involved in these polar equations. Show of hands if you understand that idea. So two different ways, doesn't matter. It does not matter in this example. I would use a symmetry because I like smaller bounds, but it does not really matter. So let's go ahead and let's go through this. You want to do it this way? So maybe you don't have to deal with the fraction. 2 times 1/2, no problem. So our area is 0 to pi. 2 and 1/2 are gone. You're going to have to distribute that. So we're going to have 1 plus 2 cosine theta plus cosine squared theta d theta. Can you double check me on that one? Hey, could you do the integral of, and you understand why we don't have a 2 or 1/2 anymore, right? We're just distributing this. Don't just square that and square that, actually distribute it. Can you do this integral of 1?
Yeah.
Can you do the integral of cosine, 2 cosine theta? That's pretty easy. Can you do the integral of cosine squared theta? Oh, really? What is it?
They were just on a roll with saying yup.
Yep.
That's, it's in the book. That's the
book. I guess it's in the book. It's all
One plus something.
Don't just say yup.
Yup.
I forgot, Mr. Leonard.
Then we use the
You forgot about your even functions when sine and cosine are both even. When sine and cosine are both
You
even.
break it up.
You do this. You don't just throw out random guesses. You use an identity to say this is 1/2 1 plus cosine 2 theta. That should ring a bell to you. Bells will be ringing, sad, sad news.
For whom the bells.
Oh, what a Christmas to have you. Do you remember that at all? I hope that you do. If you don't, you might want to refresh your memory on some of this stuff because, hey, you're going to be using this. Before you start integrating, do yourself a favor and just combine some like terms, okay? So I will integrate my 1 and my 1/2 and just make that 3/2 and then integrate it. So we're going to go 0 to pi. We're going to have 3/2 plus 2 cosine theta plus 1/2 cosine 2 theta d theta. Does that look better? Let's see if we can do all the integrals now, okay? Don't just say yep. Can you do the integral of 3/2? Yep. How about the integral of 2 cosine theta?
Indeed.
This one? Yeah, we actually just did that. It's a little substitution. We'll do it in our head. So go for it. Let's see if you guys can do it.
Okay.
I got a 3/2 theta. Did you get a 3/2 theta? Those constants don't just go away. I got a 2 sine theta. Did you get a 2 sine theta? No negatives. I got a 1/2. Okay, I got a 1/2, but then this right here, that's sine 2 theta over 2 because of our u substitution. We divide by the derivative of this little piece. That's going to give me my 1/4. Show of hands if you feel okay with that so far. Okay, we're good. What do we do now?
Evaluate.
Down
Yep, let's evaluate. Where are we going to go from?
0 to pi.
Okay, so if we go from 0 to pi, that says we're going to do, which one do we do first again?
Pi.
So 3/2 pi plus 2 times sine of pi plus 1/4 times sine of 2 pi minus, well, you know what? I'm going to cheat a little bit. Not cheat, but let's look at it. If we plug in 0, that's going to be what?
0.
That's going to be, this whole thing's going to be, this is all 0. Are you with me on that one?
Yes.
Now, if this was cosine, would I want to do that?
No.
No, because you're going to get ones out of those, okay? So this is a big old 0. Now let's do it. How much is sine of pi? Come on, quickly. Sine of pi. 0. How about sine of 2 pi? 0. Wow, that was a lot of zeros. What do we get? That's it. Our area is 3 pi over 2. So when someone asks you, do you have a large heart? You say, no, really, my heart is only an area of 3 pi over 2. It's a finite number. That was really dumb. Anyway, so the area of our heart, by the way, do I have to multiply that by 2 since I...
Yeah, what it?
Oh, okay, we already did that. So we took care of it. Whatever way you work it, I did it another way too. If you go from 0 to 2 pi, works out the same. You're going to get 3 pi over 2. Show of hands if that one made sense to you. Cool. All right, we got a couple more examples. We'll probably take care of them just next time. Okay, so the back end of our section here, almost done. What we've done on last time was we found out how to find the area that's bound by a polar curve. Do you guys remember that from yesterday? Well, the way we did it was we said, all right, what we're going to do is we're going to take the area of a little sector and we're going to integrate that. We're going to allow that sector to have an infinite number of teeny little pieces which we're going to add together. And that came up with the area of our area, well, the area of our polar curve, the area bound by our polar curve. Now what we're going to do is just extend that concept a little bit. We're going to find the area bound by 2 polar curves. So let's suppose that we got 2 polar curves. We got R1 equals f of theta, and we have R2 equals g of theta. So just 2 simple polar curves. And we're going to integrate these on a certain interval. If you remember anything about Calculus 1, this is very similar to finding the area between 2 curves. You remember finding the area between 2 curves? Do you at all? It was an integral, right? It goes from A to B, and it just said top curve minus bottom curve. That's all it was. Area under the big curve minus area under the little curve. Well, that's what this is going to look like, except think about this for a second. The area bound by a polar curve looks a whole lot like the area of a sector because the area of a sector is what we're integrating. And so this is going to be big curve minus little curve, but it's also going to fit our idea of area of a bound by a polar curve, like a sector. So let me show you what this is. So suppose we have 2 curves, f of theta and g of theta. Those are our 2 polar curves. And suppose that we know the intersection of them, or we're just going from 2 angles, alpha to beta. Then the area between these 2 curves is going to look like this. Let me refresh your memory here real quick. Area bound by 1 curve would do this. It would do alpha to beta. It would have 1/2 r squared, and then would have d theta. Does that look familiar? Don't write that down. You already have it, okay? Does that look familiar to you? Do you remember this? This was, look at this. This is area of a sector as we're letting the angle change. We're adding up all the little sectors, so adding up all the sectors as our angles change, or with little teeny angles. Show of hands if you feel okay with that one. Now, if we have 2 of these, then here's what we're going to do. basically we would say, all right, well, you know what we do? We'd have, I'm gonna kind of work with this for a little, I'll kind of semi-prove this, all right? What we would do is just say, hey, here would be the big area. So if we want to find the area of this, just the area bound by this one, we'd go from alpha to beta 1/2 of r1 squared d theta. We'd find that integral. Does that make sense? If we want to find it between a big polar equation and a small polar curve, then we would do what? Remember this? Find the area between these two curves. What do you do? So if that's the x-axis, find the area between those two curves. What do you do? Little one from, subtract little from the big one. So we'd find all of this, and we'd subtract that. Remember that? Well, we're going to do the same thing here. We'll find all the area of the big one, and we would subtract the area of the small one. I'm going to work with this for just a little bit, so you can see where this is coming from. We'd subtract, on the same bounds of integration, the area of the small one. Does that make sense? Hello, yes, no?
Yes.
Okay, so if we put them together because they have the same bounds, we end up getting alpha to beta 1/2. I can even factor the 1/2. r1 squared minus r2 squared d theta. Can you make it there algebraically? Just factor the 1/2. We're grouping these two things together. Well, let's go one step further. The one step further says that r1 is actually equal to some function in terms of theta. So instead of r1, we could write, okay, let's try this again. That was weird. Let's try this again. Instead of r1 is actually equal to a function of theta. So instead of writing r1, we could write f of theta. That's right. Instead of writing r2, we could write, that's exactly what we're going to do. And this is the formula that you guys are going to find. So we'd say alpha to beta, we'd have the 1/2. We would just have f of theta squared minus g of theta squared d theta. That's the whole idea. This is what we're working with right now. Show of hands if you feel okay with that so far. Do you guys see what it's doing? Do you see how it's taking the area of the big sector minus the area of the little sector? Do you see what it's doing? Just saying, hey, big one minus little one. That's it. That's going to give us the area between these two polar curves. Do you guys want to try an example real quick to see what this is all about? Yeah. Okay, so let's do that. So I want the area between r equals 3 and r equals 2 plus 2 cosine theta. Find the area between r equals 3 and r equals 2 plus 2 cosine theta. You know what? I'll show you how to do every bit of this, but we might want to think about what this even looks like before we get started on this. So firstly, do I have two polar curves? What do you think? Yeah. Is that a polar curve? Mm-hmm. For sure. Can you think about what that looks like? If you can't, do a little manipulation with this. So might want to think of this as r equals 2 times 1 plus cosine theta. Hey, look at that. What's r equals, y'all should know what's r equals 1 plus cosine theta?
Cardioid.
The cardioid. What's 2 times that? Just a bigger cardioid, a larger heart. Now, is this the one that's like this? Or the one that's like this?
On its side.
Yeah, that's on its side. That's right. That's the spooning cardioid is what we like to say. Well, what I like to say, because that's just funny. Anyway, so this is a bigger butt. We like big butts and count. I've been working on that one for a while.
Just waiting for the
These are the
right
brothers
moment.
they can't deny. When a cardioid walks in, what does matter? I'm not gonna go into that. Okay, so that's a cardioid. It's on its side, just a little bigger. Now, what's r equals 3? Is there a theta there?
No.
Now think about this. This says r equals 3 no matter what the theta is. R is a constant. R does not change. What does a curve look like when it has an r that doesn't change no matter what the theta is?
Sure.
Not a line. A circle. It's a circle. Can you imagine something that just has a radius of 3? What is it? It's a circle. So what this says is that our curve looks something like this. We have 1, 2, 3, and 4. Our circle would have a radius of 3. So notice this is what it's saying. It says that if you allow the angle to change and the r doesn't change, it says, hey, r is always 3, r is always 3, r is always, it's going to be a circle. 1, 2, 3. 2, 3, 1, 2, 3. So our circle would look like, oh man, I hope I get this right. Oh, it's okay. Like that. Show of hands feel okay that r equals 3 equals that circle. Now, how about the next one? Check this out. R equals this cardioid, this bigger cardioid. Now, here's what cardioids normally do. Look up here at the board, please. Typically, this cardioid would have a point at 0 and would have a point at 2. Do you remember that? It would look like this. Well, if you take all those values, those r values, and you multiply them by 2, it just doubles that. So instead of having 0, oh well, we still have 0, don't we? Because 0 times 2 is still 0. So we're going to be crossing at the pole, at the origin. But if we normally went to 2, now we're going to be going to
4.
Very good. So our cardioid is going to be outside and inside of our circle. So here's how it's going to look. Cardioid looks something, I'm going to draw in purple so you can see the difference. Looks something like this. It says normal cardioid, hey, goes like this. Wow, that's awful. So bad at this. Normal cardioid, that. An enlarged heart would do this. Would say, now we're taking all those r's and we're multiplying it by 2. So every distance is going to get a little bit further from the radius. It's going to, all those r's are going to double. Does that make sense to you? All the r's double looks something like this. Okay, you know what? I'm a little off. My heart's got a bad heart. About like that. Seems way off. Okay, let's kind of just assume, all right? Dang it. I wish I wasn't a perfectionist. I could just leave it
It's
alone.
called OCD.
Okay. Obviously, I'm not a good artist. Okay, my bad. Do you get the picture? No pun intended. But do you get the picture? The idea here. So r equals 3, circle, radius of 3. R equals 2 plus 2 cosine theta. It's a cardioid. It's just a bigger cardioid. Do you see that these curves are going to intersect? So what we're looking for is the area bound by these curves. The area bound by these curves in this instance that I want to look for is this. I'll look for that. Now, these things intersect. They intersect here and here at those 2 points. We need to find out what these are. Here's why we need to find them. Think carefully on this stuff. Look at this. Look at. Notice that our equation here deals in angles. Do you get it? It doesn't deal in x and y. It says, I need your starting angle. I need your ending angle. We need to find out the angle where these things intersect and the angle where they stop intersecting, where the intersection stops. Show of hands if you understand that concept here. So in order to do that, how would we do it? How do you ever find the intersection of 2 curves? What do you do?
Subtract.
Nope.
Never.
How do you find? Nope.
Plug in.
Usually in calculus, if you don't know the answer, say, take a derivative, and you're right. In this class, it's take an integral, but no, not this time. This goes back to algebra, actually. How do you find the intersection of 2 curves, people? You need to know how to find where 2 lines cross. Make them equal to each other. There, look at, hey, if r equals 3
Nice try.
and r equals 2 plus 2 cosine theta, could you make them equal to each other? Hey, that's going to give you where they intersect. They always happen. It always happens where if you set 2 curves equal to each other, you're going to find out where they're equal, where they cross, where the intersection is. Quick head nod if you understand that concept. It goes back to algebra. If you ever want to find out where 2 curves intersect, set them equal. So we're going to set them equal to each other to find out what these intersections are. So setting them equal, 3 equals 2 plus 2 cosine theta. So far so good? Solve it. How are we going to solve that?
Subtract 2.
Probably a good idea. So we have subtracting 2, 1 equals 2 cosine theta. Divide by 2, so I'm going to flip the sides. Cosine theta equals 1/2. Now, stop and look at your picture. This is why we usually like to have pictures here. Think about where cosine theta equals 1/2. If you know anything about trigonometry, you know that cosine equals 1/2, positive 1/2 in quadrants 1. All students take calculus. Quadrants 1, but not 2 and 3, and then quadrant 4. Does that make sense? That's where cosine theta equals positive 1/2. What is cosine theta equals positive 1/2 for quadrant 1? What's theta for quadrant 1? Very good. I had to think for a second, but yes. How about cosine theta equals 1/2 for quadrant 4? 5 pi over 3, that's right. Now, I need to clear something up for you right now. Please listen, please listen. We need this area right here. Are you with me? So, what I need to do is I need to go from here to here. We're going to be going in the positive direction for angle change. Well, the problem is if this is 5 pi over 3 and this is pi over 3, can I possibly go from 5 pi over 3 and go positive and end up at pi over 3? No, that's a bigger angle. That's a problem. Now, if I switch around and I go pi over 3 to 5 pi over 3, remember that this is going to go positively in the positive direction. So if I set up my integral from 5 pi over 3 to pi over 3, I have a problem because I can't go from big angles to small angles and still be positive. Does that make sense? If I go backwards and do 5 pi over 3 pi over 3 to 5 pi over 3, it's not doing this. It would actually be doing this. You'd find this area. Does that make sense to you? That's also another problem, unless we're looking for it. Okay, what we want to do is we want to start here and go here, but still gain angle. So still go in the positive direction. So instead of 5 pi over 3, what could I call that?
Negative.
Let's call it negative pi over 3. That way, I start here, that's still negative pi over 3, right? It's the coterminal with this. So negative pi over 3, I'm going to go positive to pi over 3. That makes sense. And I'm also going for only this range, only that angular range. Show of hands if you understand that concept. So you have to think about this. You have to think about what your quadrants are and what your picture really looks like. That's why we talked about graphing all these pictures. So we're not going to use 5 pi over 3. We're going to use negative pi over 3 because that will give me this. Did I explain that well enough for you to understand it, why we're not going from 5 pi over 3 to pi over 3? Firstly, because we can't, because that doesn't make sense. Do you understand why we're not going from pi over 3 to 5 pi over 3?
Yes.
Because that's this way. That's not this area. This is the area we're looking for. So let's go ahead, let's set this thing up, and then we'll work on the integral together, okay? So our area, we're ready to go. Where's our integral going to start, please?
Pi over 3.
Very good. Where's our integral going to stop?
Pi over 3.
What am I going to have here?
1/2.
Okay, that's our formula. 1/2. 1. I just like threes, you know. 1/2. What's going to go first?
3.
What's going to go first? Now, what's going to go first is, think about this. When I gave you the curves over here, you took a big curve minus little curve. Big here means the one furthest away from the origin. So, big curve minus little curve. What's the outside one? Is it the 3 or is it the 2 plus 2 cosine theta?
2 plus 2.
That's the outside one. So we're going to have 2 plus 2 cosine theta. Keep going. Come on, help me out.
Square.
Oh, the whole thing gets squared. That's going to be yummy. And then what?
3 squared.
Minus.
Minus what?
3 squared.
Perfect. Because that's the inside one in this case. Okay, let's double check. Do you understand why we're going from negative pi over 3 to pi over 3? Yes, no? See where the 1/2 comes from? It's our formula. It's area of a sector. We're just taking big sector, the most outside, minus little sector, the one most inside. And then we're integrating d theta. Show of hands, feel okay? Now, let's work on this one. What's the first thing we're going to do? In fact, if there's no questions, I'd like to move over here. Do you guys have any questions on this? Okay. So I want lots of space. Okay, tell me, what are you gonna do?
Go from 0 to pi over 3 and just get rid of the 1/2.
Oh, that's a good idea. Why is that a good idea? So we could do this, couldn't we? Is this symmetrical?
Yes.
We know circles are symmetrical. We also know cardioids are symmetrical about the polar axis. So that means that our area is also symmetrical. So if I wanted to, man, in order to get rid of that 1/2, that'd be kind of nice. Instead of going from negative pi over 3 to pi over 3, let's go from 0 to pi over 3. Do you guys want to do that? Let's do that. If we go from 0 to pi over 3, then we still have 1/2, and we still have all this stuff. I'm actually going to distribute this right now. So we have 4 plus, how much?
4 cosine squared. No.
Well, that's going to be up there, yeah, but what's the next thing? Let's try distributing this correctly, okay? We have 4. Then we have, how much? No. 8 cosine theta. Do y'all see where the 8 cosine theta is coming from? If you distribute, it's this times itself. So we get 4, then we got 2 and, okay, we got 4 and 4. That's 8 cosine theta. Then we have our 4 cosine theta. If you don't know how to distribute these quickly, you just square this, multiply this, multiply by 2, and then square that. So we're going to have 4 cosine squared. And then we're going to have minus 9, and then we're going to have a d theta. Now, we talked about something here real quick. You guys okay?
Since we changed bounds, wouldn't the 1/2 disappear?
We're talking about that right now, actually. So I want to make sure you guys are clear on exactly what's happening before we go any further. Do you understand where all this stuff came from right here? We're distributing this, we're just squaring our 9. Now, what we did, we changed our bounds. We're not going from negative pi over 3 to pi over 3 anymore. We're going from 0 to pi over 3. If we're going from 0 to pi over 3, that's only giving us half of the area we want. How do I make this thing fit that?
Multiply by 2.
That's right. So what this is representing, right now the way it is, it's representing this area. If I want all the area, I just times it by 2 because it's symmetrical. Does that make sense?
Mhm.
Okay, now let's start working on this thing. Couple things we can do. What's going to happen?
Put 2 and
That's kind of one of the reasons why we did this, because firstly 0 is nice to plug in rather than negative pi over 3. So when we get to the very end, I don't want to have to do that. So 0 is nice. Also, it's getting rid of all of our constants that we have outside of our integral. So we got 2 times 1/2 gone. Also, maybe we combine some like terms here. So we got area equals 0 to pi over 3 in our integral. We're going to have 4. Actually, we're not. What are we going to have? Not 5. Plus 8 cosine theta plus 4 cosine squared theta, and then d theta of all that stuff. Easy, medium, hard, what do you think? Doable?
Yes.
Have you seen this before?
Yes.
Oh yeah. Can you integrate that? Piece of cake. Can you integrate this? Piece of cake. Can you integrate this? Right now the way it is. No. Can you change it?
Yes.
Yes. Oh, you guys are the yes crowd. I forgot about that.
No, or yep.
Yep. Yep. Yep. Yep. No. 1/2 1 plus cosine 2 theta d theta. Yeah, we can use that identity. So this says, well, keep the 4. This is 1/2 times 1 plus cosine 2 theta. What's nice for us, we got even numbers. So 4 times 1/2 is 2. We go, all right, cool. We got 0 to pi over 3. We got negative 5 plus 8 cosine theta plus 2. If this whole thing is 2, then I have 2 plus 2 cosine 2 theta. I know I'm doing a couple steps at once. I'm simplifying and I'm distributing. Are you guys okay with it? Okay. why don't you go ahead and see if you can do the integral. Actually, you know what? We might want to do one more thing. What's the last thing we might want to do? Probably combine these guys. So let's do that, and then I want you to integrate it. Did you integrate it?
Yes.
How many people did integrate it? You got it. How many people did? I'll give you some more time. I want you all to integrate this. It shouldn't take you long. I don't care if you evaluate it. I want you to just integrate it. Just get the integral done. We'll evaluate this together in just a minute. So as long as you get the integral done, that's what I care about. Have you got the integral done yet? You guys over here, yes, no? Okay. So if we integrate here, we're going to have, remember it's d theta, so we're going to have negative 3 theta. We're going to have plus 8 sine theta. We're going to have plus cosine, plus sine 2 theta. Actually, what you get is 2 sine 2 theta over 2. You got 2 sine 2 theta, divide by the derivative here, but your 2's are going to be gone. Show of hands if you made it that far on your own. That's great, that's fantastic. So I'm going to raise my 2's. Now what? Say what? Where's it start?
0 to pi over 3.
It's kind of nice to have a 0, isn't it?
Yeah.
So we don't have to plug in all those negative pi over 3, so all this stuff, because that would be that'd be nasty. And we could do it. It'd be the same answer, but we don't have to now. Which one did we plug in first? So we're going to plug that in. We're going to get negative 3 times pi over 3 plus 8 sine pi over 3 plus sine 2 pi over 3 minus, now let's check this, okay? Don't make the mistake of just leaving this hanging out, okay? A lot of people, especially students who are just coming through this the first time or something, when they see 0, they just go, oh, it's always going to be 0. That's not true. If you had cosine here, it's definitely not going to be 0. Now, 3 times 0, okay. Sine of 0, okay. Sine of 0, okay. So all the rest of it's going to be 0, but you do need to check this. Does that make sense? So this is all 0, yes. So minus 0 gives us, well, let's think about that. What's negative 3 times pi over 3? Negative pi. Okay, how about sine of pi over 3? Do you know what sine of pi over 3 is? Root 3 over 2. So we have plus 8 root 3 over 2. We'll simplify that in a minute. And then sine of 2 pi over 3. What's sine of 2 pi over 3?
Root 3 over 2.
That's right. Quick show of hands, feel okay with that so far? Now, you can choose to do a couple things, but I probably wouldn't do this. I wouldn't simplify this right now because right now we have a common denominator, and we also have a common root. So if I have 8 root 3 over 2 plus root 3 over 2, that's 9 root 3 over 2. Does that make sense? So our area equals 9 root 3 over 2 minus pi. Not a nice looking area, but we found it. That's kind of cool. So the area between a large cardioid and a circle, this particular circle, is 9 root 3 over 2 minus pi. Could you find an approximation for that if I asked you to?
Yeah.
That's the whole idea. Show of hands if you're okay with this one. All right. Tell you what. The last thing that we're going to do in here, I'm going to give you some formulas on how to find arc length, on how to find area of a surface of revolution. It's going to be really similar to stuff that you've done before. I'm not going to give you examples on that. There's formulas that you will know how to plug stuff in for, okay? You know how to do integrals, right? You know how to plug stuff in, right? So it's going to be just formulaic at this point. After that, I'll show you how to find the intersection between two polar curves, which is very useful, like this sort of stuff. And we'll talk about some interesting things that can happen. So just a couple formulas at first, but do you have any questions on this before we continue? Have I explained this well enough for you guys to get it? Okay, so few other calculus concepts dealing with polar equations. And the first one is arc length. To find the length of a polar curve, you can use this formula. Arc length is the integral. Alpha, beta, those are our angles. Square root. So far, does that look familiar, the square root? Do you remember anytime we've ever found the length of a curve, we've always had a square root? In Calculus 1, it looks like this. It's 1 plus f prime of x squared under that square root. Do you remember that? That's how it looks. For parametric, it was dx dt squared plus dy dt squared. Remember that? For us, it's going to be similar to this one. What we do is we take a square root and we do dr d theta squared. So far it looks very, very similar to a parametric. And then we do just r squared. That's where it changes just a little bit. Because our r is a function of theta, we have a little bit different of an idea than parametric. But that's the idea of arc length. Feel okay with that? Could you, if I asked you to, find the length of a curve between two angles? Sure. What are you going to do? Well, the first thing you're going to do is take, not that one, okay, that's pretty easy. But like that one. First thing you do is do what? Take a derivative with respect to theta. Then square it. Not a problem. That'd be pretty easy to do, wouldn't it? So take a derivative, square it. Then, do you know how much r is?
Yes.
Sure you do. Take the r, plug it in, square it. Combine your like terms, figure out how to do the integral. It's under square root, so you might have to use some manipulation there. But that's the idea. Feel okay with the idea? Not a problem. All right, so how about area of a surface of revolution? We'll talk about the polar axis. And then about theta equals pi over 2 axis, or well, pi over 2 line. Which one do we usually call the polar axis? What is that, the x or the y?
X.
Yeah, it's like the x-axis. And the pi over 2, that's like our y. Now, of course, we don't really have those in polar equations, but we can think of them like that for this instance because I want you to really consider where we get these. Where we got all of our surface of revolution, surface area of revolution, we got this. We said, okay, if I'm going about the x-axis of some curve, well, whatever my curve is, I'm going to need to know the height of it, because what's happening here is, if you remember how this was, and if you don't, you can watch Calculus 1, I've explained how to do all of this at length and prove all of it. What happens is we take little circles, right, and we find the circumference of each circle. And we find the circumference of each circle and integrate it about the length of the curve. So you say, hey, here, what's the circumference here? Then add it up, 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 then add it up. And we do that while we integrate it across the length of this whole curve. Then what we end up getting is a whole bunch of circumferences added together gives us our surface area. Now, of course, the circumference is multiplied by a little infinitesimal width, which is how we actually get to add them up, okay? That's our integration idea. It involves a limit. But this is the plan. The plan is do circumference times length and then integrate. That's the whole idea. Circumference, what's the circumference of a circle? Oh, good. What is it?
2r squared.
No. It involves a pi and an r. It's not squared. That would be, if you square a unit, do you understand you're going to get an area out of that? I'm looking for circumference.
2 pi.
2 pi r. It's 2 pi r. So what I'm trying to do here is take the circumference times the length. Listen, do we already have an expression for the length?
Yes.
Yes, that's the length. So all we're going to have to do about the x-axis is say, okay, well, here's alpha, here's beta. I'm going to do circumference times length. The length is going to be taken care of for us already. The length is this. It's dr d theta squared plus r squared, and then of course we're going to do d theta. You guys all understand that's the length, right? So all I want is circumference times length, because I'm just adding up all the little circumferences times a little bit of width, giving us a surface area of each little kind of, it's almost like a miniature cylinder, and we allow that cylinder to change shapes. So it's 2 pi r, okay, 2 pi, well, wait a minute, 2 pi r, 2 pi, well, we don't really want r, let's not let our r's get confused here. R for polar equations stands for this distance here. What we want is the r, the radius of our little circles. What is this if I have an xy axis? What's the radius of our circle? It's y. It's y. Only in terms of us, remember back at the very beginning of polar equations, we had two definitions. We said x was equal to r cosine theta, and y was equal to r sine theta. Remember that? So instead of y, what am I going to put here?
R sine theta.
Yeah. Also, I'm going to move this 2 pi out front. I'll write it better. Now, I'm not going to give you an example about how to do this. I'm hoping that you can figure out that it's a formula. So let's look at this for a second. You already told me that you guys could find length, right?
Yes.
So if I ask you to find the surface area of revolution about the polar axis, the x-axis, think about what this means. All I want to do is find the circumference times the length. Do you guys see that this is circumference times length here?
Yes.
Look at this. Here's 2 pi r. Well, the r, in that the r is the y height, because if I'm going around the x-axis, the height of my circle, the radius of my circle, is just my y component. Y is r sine theta. So we have 2 pi radius. The radius is r sine theta because that is the height of my y. Quick hit now if you understand. That's the most tricky part here. Do you guys get that part? So circumference, 2 pi radius, y, r sine theta, times length. Hey, length. And then we integrate that. Now, can you tell me what the only difference between this and this is going to be? What do you think?
The R is
Say what now?
would be R cosine theta.
That's right, y. I mean,
Because X.
¿por qué? Because y, that's confusing.
Because it's an X.
Yeah, that's right. So if I was going around the y-axis this way, so around the y-axis, then my radius is going to be the x component. Since x is r cosine theta, we have 2 pi radius, or x cosine theta, and then we have length.
Because it's polar and x and y don't exist in polar.
Right.
Would it still?
You take your x
rotate
component and your y component and say, well, you know what, if I'm trying to figure out what my radius is, so a polar curve would look, you know what, I can do it here. Polar curve, even if I have just like this, just an arc, if I want to revolve that, I need an x component and a y component, depending on whether I'm going around the x-axis or y-axis. So if I said, all right, I want to revolve that, just something simple like that one. If I want to revolve that this way, I need to find out the radius of the circle it's going to make. So this is going to make some sort of a circle, right? Where I want to find out my radius. The radius is just the y component. So what we need to do is basically convert a polar equation into, well, kind of think it through. Think, instead of polar, let's think xy, because I'm going around the kind of the x-axis, the polar axis. I just want my component, my y component, because my y component is my height. So if my y equals r sine theta, then I have 2 pi radius, it's 2 pi y. Y is my radius, but I need it also in the form of a polar equation. That's where I get our r sine theta from. And in the around the y-axis, it's x instead of y. And so we get our r cosine theta. The length is easy. Length is what we had before. So it's circumference times length. That's basically the idea in a nutshell. I mean, I would like to prove it, but I obviously don't have time, and I've proved it before, this idea before in Calculus 1, so you can always go back and watch that. Show of hands if you understand the concept of this one. So if I had you do this, could you plug in the appropriate things? Yeah, we could find r, not a problem. Take your r, multiply by sine theta. Take dr d theta, no problem. So it's just your length. So dr d theta, square it, r squared, and then might be nasty, but you do know how to do those things. Now I want to cover one last, unless there's any other questions, any more at all with this? You sure? Okay, one more. I want to show you this example because interesting things happen when you try to find the intersection between two polar curves. I'll show you that right now. So what we're going to do is we're going to find out, without having to graph this, where these things intersect. So r equals cosine theta, r equals cosine 2 theta. Where are these going to intersect? I don't know what these things look like, or at least let's pretend I don't know what these things look like. Let's try to find out the intersection. Now, ladies and gentlemen, I asked you this already today. How do you find out where any two curves intersect? Provided they're solved for your variable, your dependent variable r, provided it's not like an r squared or something, yes, just set them equal. So if r equals cosine theta and r equals cosine 2 theta, if I want to find out where they intersect, I just set them equal and I try to solve for theta. Are you listening still? Okay, so let's do that. Let's set them equal to try to find the intersection. Now, where in the world is cosine theta going to equal cosine 2 theta? Without having to think a whole bunch of stuff here, well, and we're going to come back to this in about 3-4 minutes too. Without having to do that, let's use some identities and maybe come up with an equation that we can use. Well, the one thing I don't like how that's theta and that's 2 theta, because that's causing my brain some trouble right now. So let's change this one. So I'm going to do cosine theta. And I'm going to use that formula that we often use, but we're going to use it in reverse. Remember how cosine squared theta equals 1/2 1 plus cosine 2 theta? Well, what that means is that we can do that in reverse. So let's see, cosine squared theta equals 1/2 1 plus cosine 2 theta. If we solve that for cosine 2 theta, then we get 2 cosine squared theta minus 1 equals cosine 2 theta. Does that make sense to you? We just solved that. We use that in reverse. So this, therefore, equals cosine 2 times cosine squared theta minus 1. Now, if you don't see it, I don't blame you, but do you see this is kind of cool. This is actually a quadratic equation. Do you see it? We get something squared. We get the same something not being squared. That's why we wanted to stay away from sines and stuff. We want to make them all cosine because right now if I solve this for 0 on one side, I can get that. Now what's interesting is this is still factorable just like anything else. It'd be like doing 0 equals 2x squared minus x minus 1. In fact, you could do that. Just call that x for now, factor it, put your cosine back in. So if you factored
Not
Yeah, I
theta,
was
sorry,
like, why'd you
zero.
put theta?
Because I just got in the habit of it. 2x, what is it? 2x. Do you know it? I'm pretty sure it's that, but you can double check. That would give us 2x squared minus 2x plus x, that's minus x, and then minus 1. Can you verify that that's the correct one? Okay. Well, now that we have cosines instead of x's, we get 0 equals 2 cosine theta plus 1 times cosine theta minus 1. Just from our basic factoring. Now what's interesting is that the zero product property, that always works for us. So if we have a product and we have that product equal to 0, what that says is that each of those factors has to equal 0. Let's deal with this one first because it's going to be a little bit easier for us, all right? Let's solve that. How would I solve it?
Add 1. Add 1 divided by 2.
Cosine theta equals
1 half.
1. Now, this one's easy, okay? Cosine theta equals 1. You tell me right now, if cosine theta equals 1, how much is theta?
0.
Very good. 0. You with me? Okay, now think about this for 2. Look back up our original equation. Do you remember, we want points, right? We want intersection points. Intersection points look like this. They look like r thetas. You get me? We now have a theta. We need an r. This is going to be an easy one, but do you understand that we're not done right here? We just have, this is like saying, hey, find out where the lines intersect. And you say, they intersect at x equals 3. Does that give me a point? No, it tells me somewhere in infinity at x equals 3 they're going to intersect. I don't want that. I want to know the angle and how far out to go. I don't want, hey, they intersect at theta equals 0. Cool, where? That doesn't help me at all. I want to know where. I want a point. Do you get the point? Okay, so 0. Now look at this. If r equals cosine theta, look down here. How much does cosine theta equal?
1.
How much does r equal? Cosine theta equals 1, therefore r equals 1. So from here, r equals 1. We now have a point. We have a point. Which one comes first, the r or the theta? So 1, 0. These are going to intersect at the polar coordinate of 1 and 0. 1 and 0. An r of 1, an angle of 0. So it says, hey, angle 0, go out 1. These things are going to intersect right there. Show of hands if you understand that one. Okay, now let's work on this one real quick. Do you understand that here we're going to have cosine theta equals negative 1/2? Yes, no? Okay, if cosine theta equals negative 1/2, cosine is negative in quadrants 2 and 3. Very good. So cosine's 1/2, where? At pi over 3. So if it's a pi over 3 for 1/2, it's going to be 2 pi over 3 for negative 1/2 and 4 pi over 3 for negative 1/2. So these thetas are 2 pi over 3. You can check your unit circle if you want. And 4 pi over 3. Show of hands, feel okay with that one? Are you sure? Now, is my r going to be 1 for these points as well? What's my r? Look up here. What's my r? You got it. Cosine theta equals r, yeah? So if cosine theta equals negative 1/2, that means r equals negative 1/2. And so we get 2 points here, but they're both going to have the same r. We get negative 1/2 2 pi over 3. And we get negative 1/2 4 pi over 3. What I want to know is, does that make sense to you? Show of hands if it does. You're like, okay, that makes sense. These are weird, yeah, because you have to go 2 pi over 3, but then go negative 1/2. All right, so it's in quadrant 4. And this one says you go 4 pi over 3. Can't even do that. And that's negative, so it's in quadrant 1, actually. But that's what those intersections are. This is right on the polar axis. Do you guys feel okay with that one? So use an identity, find an equation, solve it, then just don't forget that you need to find your r. You don't just give me thetas here. Theta is 0, sure, but r is 1, so 1, 0. Theta is 2 pi over 3 and 4 pi over 3, but that also, they both work with the r, because theta is r, of negative 1/2. So we have negative 1/2 2 pi over 3, and negative 1/2 4 pi over 3. Now, the last bit, this was not that interesting. This is what makes it interesting. You ready? Plug in cosine of pi over 2. What's cosine of pi over 2? 0. What's cosine of 3 pi over 2? Good, I was supposed to sleep for a little bit. Okay, good, very good. All right. Do pi over 4. So that was for this one. Do you understand that you are going to have an r of 0? Do you get that point? So if I plug in, so this is kind of this is the interesting part. So if I do theta equals pi over 2 or 3 pi over 2, I get 0. With me? That means I'm going through the pole. I'm going through the origin. You follow? Do this. Plug in pi over 4 here. It's 2 times pi over 4. What's our r? Weird, okay. Plug in 3 pi over 4. 3 pi over 4 times 2 is 3 pi over 2. What's cosine of 3 pi over 2? I get 0 here. Did we have an intersection of r equals 0 anywhere up here? No, this said r equals 1. This said r equals negative 1/2. Yet, we know for sure that both of these curves are going to go through the origin at some point. Did you get that? Why it doesn't show up is because they go through the origin at different times. So what's weird about these polar curves is that even if you solve it all the way down, we don't make any mistakes here, you can still go through the same point, but at different times. So the angles aren't the same when they hit that point. Because here we're multiplying those angles times 2. That's what's weird. So we do have another intersection. So one more intersection. Intersection happens at negative 1/2 2 pi over 3. Intersection happens at negative 1/2 4 pi over 3. Intersection happens at 1, 0. Intersection also happens at r equals 0. Because they're both going through the origin right there. Isn't that interesting? That's kind of cool, right? Weird, just different times. Show of hands if everything made sense up until this last little part. Did this last little part make sense? Did it blow your mind? It should blow your mind a little bit like, whoa, that's weird. Because it's almost like parametric. It's just happening at a different time. It's reaching that point at a different angle. Anyway, that is it for this section.